Hi everyone. So today we're going to talk about the difference between mass and weight. So mass is a quantity that describes inertia, right? We learned that when it came to Newton's first law. So another working definition of mass is that mass describes the amount of matter in an object. You probably learned this definition in chemistry class. Mass is measured in kilograms, at least that's the SI unit, so that's what we'll be using in class. Mass is a scalar quantity. It only has magnitude. It has no direction, right? It doesn't make sense for it to have a direction. And mass is also an intrinsic property of the object, right? So it doesn't matter what forces are acting on the object or where the object is, it's going to have the same amount of mass. It's going to have the same amount of matter. It doesn't matter what force is acting on it, it has that same amount of matter, so it's going to have the same mass. Weight, on the other hand, is a force, right? It's actually the force due to gravity by a planet. So this quantity is a vector, not a scalar, because forces are vectors. And this force vector, so weight, is going to point towards the center of the planet, or straight down, colloquially. And this is going to be measured in newtons because it's a force. Mass and weight are not the same thing. That's a really, really important concept. I know we already touched upon it a little bit in class, but they're not the same thing. A lot of times we mix up terminology when it comes to weight and mass. For example, you might say an object weighs 4 kilograms. No, it does not. It has a mass of 4 kilograms, right? So be very careful with your vernacular when it comes to lab reports and free response problems. I and the AP exam are both going to grade harshly on that, right? Although they're not the same thing, they are related, right? So the force due to gravity, or the weight of an object, is going to be equal to mass times the acceleration due to gravity, right? So here you can see that weight and mass are actually going to be directly proportional, with the acceleration due to gravity being our coefficient. So the weight of an object is going to be independent of its state of motion. Right, so this equation, the weight of an object, doesn't matter if the object's at rest on a table or sliding horizontally or accelerating. It doesn't matter. Weight is always going to be mass times the acceleration due to gravity, right? So because weight depends on g, and g changes from planet to planet, right? So g is 9.8 meters per second squared only on Earth, right? On other planets or other celestial bodies, so for example the moon, on the moon, the acceleration due to gravity is about 1/6 the value of g on Earth, right? So therefore weight can't be a fixed quantity. It can't be a constant quantity. If I was standing on Earth, I'd have a different weight, and then I would be standing on the moon. Though I had the same amount of mass, just different weight. Now when it comes to measuring mass, we can use a pan balance. Right, so this basically used the idea of balancing an unknown mass with values of known masses and getting the pans to balance. Right, you might have used this in chemistry class when measuring chemicals. So although this pan balance does use gravity in a sense in order to function, because gravity is actually what causes it to balance, right? The force due to gravity. It doesn't matter the value of g when you're using this pan balance, right? It's going to give the same result on any planet. Now when it comes to measuring weight, we're going to use a spring scale, and that measures weight. Here actually we'll be dealing with spring scales that look like this often in class, where it has a hook at the end. We'll also be using a spring scale. It doesn't look like this, it has an automatic read, but we'll have spring scales also similar to this. But basically what this system does, or this method, what it uses is the fact that at equilibrium, the sum of the forces is 0. So if we're dealing with an object, its weight acting downwards, we're going to have the force of a spring acting upwards. So if we kind of looked inside this balance here, we might see something like this, where we have springs pushing upwards, literal springs. Now the spring force is actually going to be proportional to the distance the springs are compressed, right? We'll talk about that later, not in this unit, but we'll deal with that in detail. So because of that, these springs are going to compress different amounts depending on where they are, depending on what the value of g is, right? So basically, if we're dealing with different planets, we're going to have different weight measurements when it comes to these spring scales. But actually, it's not just limited to other planets. We can actually see this here on Earth as well. So this is where the idea of apparent weight comes in. So let's suppose, actually let me start off with giving a rudimentary definition of apparent weight. So apparent weight is basically what a bathroom scale would read, right? So it's going to be the normal force acting on the object on the scale. One way to always think of what a scale is going to read, you can think of this, a bathroom scale as a normal meter. It measures the normal force, right? Though that's not a very nice definition, we can roll with it. So let's suppose a person is standing in an elevator that's at rest, right? So the person in this elevator is at rest, so the net force is going to be 0 because we're in equilibrium, right? So if we draw, this is actually not a complete free body diagram, but we're here diagramming the forces. So we have the force of gravity acting down and the normal force acting up. So it's the force of the spring scale acting up on the person's feet. So because we're in equilibrium, these forces are going to be equal in magnitude, and the scale reads the person's actual weight. I don't know why I wrote rate there. That should read weight. Probably because I can't say the words verbally. I can't type either. But now let's suppose the elevator is accelerating upwards. All right, so here's a diagram of that situation here. So we have an acceleration, so we have a net force. Because we're accelerating upwards, our net force is going to be pointing upwards, right? That's remember that definition from Newton's second law. The acceleration vector and the net force vector point in the same direction. Right? So because of this, our normal force must be larger than our weight. So the scale is going to read a larger number than our actual weight. And this is our apparent weight is actually larger than our actual weight. So this is kind of like why you're going to feel heavier when you're accelerating upwards. So say you're in a roller coaster and you get shot straight up or even at an angle, that's fine, but you're accelerating, you feel heavier, and this is why your apparent weight is larger. Now, if we had this situation where the elevator is accelerating downwards, in this case, acceleration is pointing down, so net force has to be pointing down. So in this case, our weight force has to be larger than our normal force. Right, so then our scale is going to be reading a smaller value than our actual weight. So therefore, our apparent weight is going to be smaller than our actual weight value. So this is why you feel lighter when accelerating downwards. So say you're going, so on that same roller coaster example, you're going downhill, you're accelerating downwards, you feel lighter. Your apparent weight is smaller than your actual weight. So let's say we're in this elevator and the cable breaks. So don't worry, there's a safe way to decelerate at the end so the person doesn't get hurt. So now this elevator is in free fall, right? So what will the scale read when we're in free fall? So one way to think about this is looking pretty much at our previous slide here and kind of thinking about limits, right? What would happen as our acceleration gets bigger and bigger to the biggest value it could be? That in a sense here is we're doing the same thing by saying we know our net force is mass times acceleration, and in free fall our acceleration is going to be equal to g, 9.8 meters per second squared on Earth. So therefore our net force has to be equal to m times g. And m times g, oh, whoa, that's our weight. So our net force has to be our weight. So there can't be a normal force. If there were a normal force, then our acceleration wouldn't be 9.8 meters per second squared. It'd be some smaller magnitude, right? So in this case, our scale is going to read 0. The apparent weight of our person is 0. So this is a working definition of weightlessness. So an object that is weightless is going to have no apparent weight. So the object still has a weight. It's equal to m times g, but it has no apparent weight. So this is another terminology that's also often confused. Weightlessness does not mean no weight. They still have a weight, but they're just in free fall. So that's what I have for you guys. Thanks.